are from Group 7. Now we are presenting for our course EMJ 22004 Analog Electronic Lab 2. And my name is Li Jihong and my partner is Ted Julian. Okay, now this one is our content, have objective, type of operation, amplifiers, simulation, result, and conclusion. Now is objective. The objective of this lab were to understand 5 OPM configuration, compare the theoretical and simulated result, and determine the effect of non-ideal component. Now we will go through simulation and circuit demonstration. This one is our type of OPM, A, B, C, D, and E. Now is the first one, inverting amplifier. Our calculation for R2 over R1 have a gain of -33. However, the simulation show the output clipping at approximately ±14.7 watt. This one will be shown in the result and analysis. So now I will shortly briefing the circuit and parameter. So you will see this one is the circuit from the LT spice, and this one is the value of R1 and R2. So I will just go through one by one, so the slide only. So now I will just pass through to the result and analysis. This one is our result of inverting operational amplifier. So you see this one is 1 watt and this one is 30 watt. And this one is a comparison for our theory calculation and the simulation result. This significantly division is explained by the non-ideal characteristic of power supply saturation. Since the calculation is -33 watt, exceeded the OPM ±15 watt supply, the signal was tripled. So the demonstrated critical trade-off, high gain is constrained by the supply voltage limit. So now I will explain to the result of non-inverting operation amplifier. Our calculation is R2 over R1. Oh, sorry. Next is the non-inverting operational amplifier. Here's our result. Show the excellent agreement. Both calculation and simulation is same. Is 11 watt. So this confirms the formula AV equals to 1 plus R2 over R1. The result match perfectly because 11 watt is safely between the supply rails, allowing the OPM to operate ideally in each linear region. So for this part, I will get my partner to explain to us.
I am Tazian, and I will now cover the dynamic circuit, starting with the integrator. The circuit successfully performed its function, converting the square wave input into the expected triangular wave output, while the integration function was ideal. We must discuss the 10 mega ohm resistor present in the feedback loop. This component is essential for DC stability. Without it, tiny input offset voltage will be integrated, causing the output to quickly drift and saturated at the rail. The resistor introduced a trade-off, sacrificing ideal low frequency integration for crucial long-term stability. The differentiator circuit correctly produced the square wave output from the triangular input, validating the rate of change operation. Now consider the 100 pF capacitor across the feedback resistor. This small component is critical for noise immunity. An ideal theater amplifier high frequency noise extensively. The capacitor limit this high frequency gain, acting 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 as a low pass filter to ensure stability and reduce noise. A necessary trade-off to prevent the output from being overwhelmed by noise.
Okay, now I will explain to the result of summing amplifier. Our final circuit is summing amplifier, and we calculated the weighted sum output of -6 VP, which the simulation closely verified. This confirmed the core principle of weighted algebraic summation. However, if we significantly increase the frequency, the OPM will face the constraint of its limited slew rate and bandwidth, leading to signal distortion or reduced gain. This represents a performance constraint inherent to the non-ideal LM741. And now is a conclusion.
In conclusion, Lab02 successfully achieved its objective by verifying the operation of 5 fundamental op-amp circuits. We confirmed the theoretical gain equation and observed the mathematics function of the integrator and differentiator. Crucially, the experiment demonstrated the significance of non-ideal op-amp characteristics. We identify the supply voltage constraints leading to output clipping in the high gain inverting circuit, and understood the need for compensation component for stability and noise limiting. This lab has ultimately strengthened our understanding of analog electronics by illustrating that practical design requires careful consideration of real-world limits to ensure stability and reliable signal performance. Thanks you.